Climate change is affecting the critical infrastructure that plays a key role in our national security. Lawrence Livermore National Laboratory is working to advance understanding of the global climate system, develop technologies to reduce accumulation of greenhouse gases, and pursue the domestic production and supply of affordable, clean energy. To fulfill its mission, the lab is using its tools as a national security lab to address the impacts of climate change and increase the resilience of our infrastructure.
Climate and weather just affect everything that we do.
From the infrastructure perspective, we view climate as a way of generating alternative future weathers. We care about what the weather is going to look like in the future so we can actually mitigate the issues that might crop up then. So the climate models provide us with those alternative futures.
Right, so we can make choices now in terms of what we build so that when the future comes, we'll be better prepared. Livermore's been a real center of expertise on supercomputers for a long time. Climate is one great example of a problem that needs that type of intensive capability, and solving the electrical grid and how to balance all different sources of energy and transmission is another one. So we have both these capabilities at the lab, and we realize that by bringing them together, we can create a useful and powerful tool to try and make the electrical grid more stable in the future going forward.
Yep. Nothing to add, that's perfect.
Machine learning is a new set of tools for calculating things and analyzing things. Resolution is important. We need detail. The wind here versus a few kilometers away makes a difference, and generally the models don't capture that or calculate that. An alternative way to do it is to teach a machine learning system or give it lots of examples of how the high resolution data looks like, possibly observational data, and then give it lots of information about how the models looked in comparison, and then the computer can run the machine learning training algorithms and figure out how to take the low resolution information to give us the detail that we need for doing the electrical grid modeling.
Yeah, we've been working on electrical grid models for the past approximately 15 years. Which really started kicking in full gear in the early 2010s. And the program has grown exponentially ever since. Climate models, as I mentioned before, I view them as producers of alternative future weather projections, and weather is everything to the grid. There's a lot of work that we actually take the output of the climate models and feed them into what are called fragility curves that actually produce direct grid impacts. But if we don't have those inputs, we can't actually do anything in terms of projections for what the grid might look like in the future. And not just tomorrow or maybe a week out, but in 30 or 50 years out. And that's critical for us to actually operate and predict.
That it's not sufficient for me as a climate scientist to calculate the rain, the dryness, etc. I need to calculate the things that are needed by the electrical grid model because that's what impacts them. The wildfire, the flooding, the wind, the sunniness on the solar panels, all those sorts of things. So that's why it's so crucial to have electrical grid experts that we can understand what it is that the electrical grid needs and where it's important, what resolution we need, and all those things only come by working together. So that's why it's been such a pleasure for me to work with JP and the other electrical grid infrastructure experts to learn that whole dimension of it and how we can bridge the gap between the climate modeling and the infrastructure and potentially other impacts in the future.
Yep. Just kidding.
For more information about LLNL's multidisciplinary approach to climate and energy security, visit llnl.gov/purpose/missions.